We use the speaker.
Oh, which speaker?
Yeah.
It's more.
Hey, can you see my screen? Can you see my screen? Or no? Can you see my screen? Okay, good.
Taiwan je.
So is it okay? Everything okay?
Ini berapa?
Everyone online, do you can see the slide clearly?
Yes.
Need to ask them whether they here or not. Oh, congratulations.
All good?
Please,
Okay, great. So we
Oh, you can be Iraq.
we wait for another
no problem.
10 minutes.
Sure.
So
No.
we start at 10:15.
10:15. Okay, no problem. Yeah, we can wait. So your author was WCC.
WCC. The most senior in WCC.
Oh, you are?
And deputy director.
Oh, very high up.
Director is associate professor.
Uh-huh.
Currently he's in shop.
Oh, I see. Okay. Oh.
Also, Dr. Bruce, he is Dr. Bruce, one of the WCC member attending conference in Taiwan.
Taiwan ada conference.
Recently?
Yeah.
That?
Yeah.
Oh, GlobeCom. There's a GlobeCom.
Yeah.
Yeah, GlobeCom is big. Also, TSCC.
Under communications.
Yeah, Global Communication Conference. But that's like wireless communication.
Travel is the one WCC member, but just now, the one that
Oh, yeah. His name is also Kamal.
Rukama. Name is
Same surname.
Irahim is Abdul Rahim.
So you guys have the same
Yeah.
first name and surname.
Same father but different.
Same father, different mother.
My first name is Razadi, the name is Nah.
Oh,
Bin is son.
oh.
It's not related to Bin Laden or whatever. Bin is son.
Oh, I see. Oh, platonic. Okay. Oh, so you went to.
And project.
So you're doing platonic over.
Right now, one of the current project is the FSO, basic.
Oh, okay. So that's like using
Yeah.
point to point.
Point of
Line
that.
cycle. Very interesting.
So if you have a click or brain Taiwan working on that,
Sure. Yeah. Thanks. Yeah, we do have some professors working on optics and fiber for fiber.
I'm not doing fiber. Yeah, it's just
Over the air.
Yeah.
Essentially, that's for satellite, right?
Yeah.
Dipole.
Yeah.
We want to do this very high speed, and in the outer space, dipole, it's only paid by certain parts. power too. So yeah, so basically, since there's no like water. Mine's like.
Especially for future generation, 6G, for example, the frequency become higher
Right.
cell
And also whole run.
smaller. So thinking of using a fiber, we can
Right, exactly. Yeah, and also this light conflict. Modulate the light at very high speed. Like high speed. But then you can. Very interesting.
So your talk will be 1 hour.
About an hour, yeah. Probably make it.
Then we have 30 minutes to Q&A.
And I can also introduce a little bit of my house.
Yeah. And then after this event, we go to the BCC.
Okay.
Discussion.
Yeah, that was.
Then after that we go. The lunch, you may go to Kamal group.
Sounds good. So your labs are over close by.
Yeah.
This is such a huge campus.
Yeah.
Well, how many students?
Electrical engineering.
One 500.
One intake.
1 year.
One enrollment.
From 500. Undergrad. For 1 year.
We
1 semester.
enrollment is twice. We have a year twice enrollment.
So
So that means 1,000 per year
1,000.
per intake per enrollment.
So huge. Wow. So okay. So you're like freshman. Yeah. Right. Sure, it has 1,000. Total 4,000.
We have currently we have is it 4 programs. Electronics, mechatronics, biomedical, and power. I think power. So last time we do have a telecommunication program. We have like now we want to start again for the telecommunication.
Oh, that will be a special program.
We do have a master program for telecommunication.
Oh, I see. Nice. And you also have PhD, right? Yeah. Some students are professional now.
So also, senior, I mean, Dr. Haizan.
I heard that.
Yeah.
I was having.
Communication with has been.
No, I have not. It's not.
I know.
You can. He is a student.
Yes.
He's not.
Yeah, I was of 2 or 3 hours.
Friendship. If someone.
Oh, okay.
Oh, sure, it's not.
Jadi dia rasa dia.
It's not.
No. Okay. Assalamualaikum warahmatullahi wabarakatuh and very good morning. Welcome distinguished lecture series. So we are grateful to have all of you here today, both physically and online. I hope this event will be insightful and inspiring for everyone. So this event is jointly organized by the IEEE Malaysia, IP, MTT, DMC Joint Chapter and the Wireless Communication Center, WCC, State and Malaysia. First of all, my name is Razali from WCC here. And this morning, I wanted to deliver the welcome remark on behalf of the WCC Director, Prof. Is currently attending a workshop. Actually, I would like to mention here, actually, Prof. Kamal is actually the most suitable person to give this welcome speech. As he was the one who proposed of Michael.
Thank you, yeah. Thank you for the
Prof.
invitation.
Kamal actively involved in the IEEE Malaysia Joint Chapter. So today we are privileged to host a distinguished expert in advanced electromagnetic material of Chung Michael.
Yeah, Michael.
Or we call it Prof. Michael.
Sure.
From National Taiwan University. I would like to give a brief introduction of Michael. I hope because I get from.
No problem. Yeah. Or you can just make it very short. That's also okay.
Prof. Michael received his bachelor degree from NTU, National Taiwan University, followed by master and PhD from University of California, Los Angeles. For joined NTU, he served at Wayne State University.
Yeah.
And
Rutgers. Yeah.
Rutgers University. Michael is internationally recognized for his pioneering work in high electromagnetic, metamaterial, microwave, and millimeter wave circuit, internal system, data sensing, and advanced wireless technology. His outstanding contribution have earned him prestigious awards such as the NSF Carrier Award, DARPA Young Faculty Award, Director Fellowship, and Rutgers Trustee Research Fellowship. He also contributed deeply to the IEEE Microwave Theory and Technology Community, for technical committee and editorial group. So this morning, Michael will be speaking on sensing, tracking, and secure communication with artificial electromagnetic material. So I think the talk will highlight cutting-edge development, futuristic application, and real-world impact of next generation electromagnetic material technologies. So we hope today's session will spark new ideas and encourage a meaningful discussion and strengthen collaboration among academicians and students. So thanks again for joining us. So ladies and gentlemen, please join me to welcome the Associate Prof. Dr. Michael.
Here.
So the first
Thank you. Yeah, thank you very much for the kind introduction. Yeah, thanks again, Professor Kamal, for inviting me here. Yeah, I was really impressed first time being in Johor. Actually, probably also first time in Malaysia. So, or second time. Yeah, maybe first time was when I was very little. But yeah, I was very impressed by such a huge campus and. Oh, sorry. Oh, is my sound okay? Okay. Yeah. So my topic today is going to be related to nanomaterials, and particularly, the talk will be talking a little bit about some applications for nanomaterials So yeah, without further ado, let me just jump to, yeah, so yeah, it has some delay. But yeah, so perhaps one of the oldest so-called materials is this Lycurgus cup. So it's sitting in the British Museum, and then it was basically from 4th century. So the interesting property about the cup is that when you shine light from different location, it will appear in different color. So let's say if you put the light source inside a cup, right, it will appear the red color, like the right hand side as it shows. But then if you just if you just shine the light from outside, from the daylight, actually, it will appear in green. So people at that time doesn't really know what is the reason for this. Now until recently that scientists actually discovered that the cup is made of ruby glass, and the glass contains a lot of the silver and gold particles, and this at the nanometer scale. So it's very similar to our visible wavelengths. So therefore, it will cause this surface plasmonic effect, which will result in this property that very similar to a frequency selective surface. Yeah, so therefore, it has this frequency selective property. So different spectral component basically will be filtered out from different locations. So that's why we can see this kind of different color. So yeah, so this can be considered one of the oldest so-called material or artificially engineered materials. Yeah, so coming back to our fundamental EM class or EM field, I'm sure that most of us have taken the class, right? So we know that when EM waves is propagating inside materials, the property is governed by, the material's property is governed by its permittivity and permeability, epsilon and mu. So then when we incorporate some periodic patterns, right, we can engineer the materials and then we can make it into a effective, we can engineer it into effective epsilon and mu. And then at some frequency range, this epsilon and mu can even be negative. So these properties cannot be really seen in nature, right? So we refer this as metamaterials. Meta in ancient Greek term is called the meaning is to go beyond, right? So yeah, so it's going beyond the conventional materials. Yeah, so therefore we refer these kind of materials with unusual EM properties. We call this metamaterials or artificially engineered materials. So then, if we further take a look at its property, then we also know that when waves is propagating inside materials governed by the very well-known Maxwell's equations, and then time varying case, like we know electric field and magnetic field, they're coupled with each other, and then the phase velocity direction or the propagation direction can be determined by when you use your right hand to do E cross H, right? So when you do E cross H, your thumb will be pointing to the phase velocity direction or the wave propagating direction. And then, so if it's a plane wave, then beta will have a linear relationship with the frequency, right? It's a function of epsilon and mu as well. And of course, from Maxwell's equation, we know in time varying case, E and H, they are coupled with each other. So time varying E field will generate time varying magnetic field and vice versa, right? And then actually, if we also have taken the class of microwave engineering, also know that there's a very similar analogy between transmission line and plane wave, right? So yeah, so basically along the transmission line, we will have voltage wave and current wave, right? Now, if we look at the transmission line circuit model, it contains this series L and shunt C. And we can also define its propagation constant in terms of L and C, and it also has a linear relationship with the frequency omega. And then the governing equation in this case is so-called Telegraph's equation, where the voltage wave and current wave, they're coupled with each other. And if you compare these two equations, Maxwell's equation and Telegraph's equations, you will see they are very similar to each other. If we just simply map E field to V, right, and then H to I, and then mu to L, and then epsilon to C, they have exactly the same mathematical formulation. So this means that, okay, then if we can use some periodic structure in EM materials to synthesize the so-called metamaterials, then we should be able to also use transmission line approach to synthesize these metamaterials. So yeah, indeed. So if we take a look at the conventional right-handed transmission line, this is the one we have just briefly talked about, right? So we know that when we plot this dispersion curve or the so-called beta omega relationship, beta will be a linear function of frequency, and in this case, it will follow the right-hand rule, meaning that the phase velocity direction can be determined by using your right hand, and then you do this E cross H, and then the thumb will be pointing towards the phase velocity direction. So what happened if we swap the two components? Now, if we have a series C and shunt L, right, then what will happen? So if we still derive the propagation constant, actually Z now will become 1 over j omega C, right? And then Y is the admittance of this L, so it's 1 over j omega L. So if we multiply them together, it will become a purely negative quantity. Yeah, so therefore, now it's no longer following the right-hand rule, right? Because beta now is negative, so we have to use our left hand to do E cross H. So now your thumb now will be pointing to the opposite direction, right? So it basically refer to a backward wave propagation. Yeah, so therefore we refer this as left-handed transmission line, or since it also has this exotic property, so we can also refer this as a transmission line version of man material, or man material transmission line. Yeah, so then in this case, you see that beta is not a linear function of omega, it's also purely negative. So, but in reality, we want to realize a purely left-handed transmission line is pretty challenging because we will always see the parasitics come into play, right? So together, in addition to CL and LL, so the subscript L refer to the left-handed component, and then the subscript R refer to the right-handed components. So together we will have the 4 components, right? This LR, CL, and LLCR to form this so-called composite right-left-handed transmission line, or simply just CR transmission line. So now we can still derive its propagation constant. It's just that Z is now becomes series LC, right? And then Y is the shunt LC. Yeah, and then so beta now will become a little bit more complicated. But interestingly, what we'll see is that at low frequency, so this S of omega is a sine function. So at low frequency, beta will be negative, but then once you increase the frequency, beta can be positive. And of course, when it's in between, it can at some frequency it can become 0. There's also another interesting case, we call it balance case, where we have same frequency of this series and shunt resonance, right? If this happens, actually we can decompose the circuit into a right-handed beta followed by left-handed beta. So yeah, meaning that we can further simplify the circuit. And yeah, this condition is particularly useful if we want to realize a leaky wave antenna. So yeah, taking a closer look at the dispersion diagram. So here we can first divide the region into positive and negative beta, right? So if it's positive beta, we refer it as a right-handed region, and if it's negative beta, we refer it as a left-handed region. So conventional right-handed transmission line, of course, will be in the right-handed region, and then it's also in the guided mode or guided region. So this can be defined by drawing these two so-called air lines, right, with the slope of the speed of light. So yeah, when the phase velocity or the slope, right, is smaller than the speed of light, actually it will be in the guided mode. And when when you see the phase velocity is larger than the speed of light, so in the center 2 regimes, actually it's called a radiation region or the fast wave region. So the reason that during this region, the wave can leak out or can radiate is because if we break down the vector components, as you can see here, so if beta is smaller than K0, this vertical K will be a real number, right? So this will happen when phase velocity is larger than the speed of light, right? So yeah, so therefore, when phase velocity is larger than the speed of light, we refer to it as a fast wave region or radiation region. But on the other hand, if phase velocity is smaller than the speed of light, then actually the wave will not radiate to the free space. Instead, it will just be confined in the transmission line structure. Yeah, so then if we draw the CR transmission lines dispersion diagram, if it's an unbalanced structure, then we'll see the dispersion curve will come across the 4 regimes. It just in the center, we'll see a small band gap, right? And this is because we have different series and shunt resonance. But now if we have the same resonance frequency for both series and shunt LC, then we can close the band gap. And this is, like we just mentioned, is particularly useful if we want to have a smooth transition, right, during the fast wave regime. And once we have that, then if we change the frequency, then actually we can have a smooth transition for beta. And at the center frequency, right, as some frequency in the center, beta can actually be 0 as well. So then we can utilize this property to form so-called leaky wave antenna if we operate this transmission line in the fast wave region. So some advantages about the leaky wave antenna is that it can provide a very simple beam scanning capability. right? And then because we just need to change the frequency, and then you can also provide a decent directive beam, suppose the aperture is large enough. But conventional liquid antenna, of course, because beta can only be positive, so it has very limited scanning angle. However, on the other hand, we use CR liquid transmission line to realize liquid antenna, because beta in this case can be both negative or positive, so it can have a wider scanning range. This can also be seen from this vector relationship shown here. If we define our main beam angle as this theta here, so theta from this trigonometric relationship, we can see that theta is arc sine of beta over k now, right? So because now beta can be from ideally from negative k0 to positive k0 through a 0 point at the center frequency. So indeed, this theta, right? This theta can scan, ideally can scan from negative 90 degrees to 0 and then further down to 90 degrees. So it will provide a pretty simple backward to forward beam scanning capability, as you can see in this figure, and with a very simple feeding structure. So here is one of the earliest prototype fabricated by Professor Ito's group. So as you can see here, when they try to realize the CR transmission line, this is the unit cell that they use, right? It contains a interdigital capacitor to form the CL, right? And then also a stop inductor to form the LL. But then because of the natural parasitics, so if we look at the circuit model, it will still have this fundamental circuit element. And then if we cascade multiple of them, we can realize a CR transmission line. And furthermore, if we operate in a fast wave eugenic conformal antenna, so then, they measure the antenna pattern, right? So indeed, you can see this frequency scanning capability. If you scan the frequency from low to high, indeed, you see the main beam can be scanned, right? All right, so recently we have also used this property of CR transmission line to form a very wideband material antenna array using the so-called integrated passive device technology, or IPD. So this IPD technology, it's a semiconductor technology, but it's purely passive. It doesn't have any like transistor with it. But the advantage of this is that the resolution can be pretty good, down to micrometer resolution. So we utilize this to form a 5x5 metamaterial antenna array. So if we look at the unit cell itself, it's like a bow tie antenna, but then in between they have this metal insulator metal capacitors. So basically the like equivalent circuit model is very similar to a CR transmission line, owing to this traveling wave property. And we flip trip this IPD antenna array onto a multi-layer printed circuit board to further enhance the impedance bandwidth. And as you can see here, this is a VSWR. So roughly it can go from 18 gigahertz all the way up to 100 gigahertz with a very wide impedance bandwidth. And we also measured the pattern inside an anechoic chamber. And as you can see, we pick up several key frequencies. So I think in this case it's 26, 39, and 77 and 94. So these are some key frequencies for 5G and automotive radar bands. They are all, as you can see here, the pattern is all pointing towards a broadside direction with a pretty decent gain. So of course, the gain is a function of frequency. So the higher the frequency is, you will see an increasing gain, about 4 or 5 dBi at the higher end. So switching gear a little bit, we know that recently there's an emerging area, right? It's called reconfigurable intelligent surface. Yeah, I know Professor Kamel has also been working a lot on this meta surface stuff. We know that meta surface that indeed is also consisting of a lot of unit cells, right? So basically, if we have a different phase profile across the meta surface, right, we can control the reflected beam, right? So basically it's like a reflect array. Then if we have different phase profile, then we can control the reflected beam. But in addition to this, right, that's one way to modulate to control the reflected beam. But in addition to this spatial modulation, if we also incorporate the time modulation, right? So meaning that not only, so in this case, we have a binary modulation. You can imagine 0 is 0 phase and 1 is 180-degree out of phase, right? So not only the phase profile is a function of space, but if we also modulate it in time, then actually we can generate harmonics, right? Depending on this, we call this space-time modulating matrix or space-time coding matrix. Yeah, so this basically will exhibit a pretty interesting property that if we inject a fundamental tone from outside, then depending on this space-time modulation, actually will generate the harmonics and can enable different applications on this. So yeah, this also makes us think that can we also realize an antenna version of it, right? Because we know that if we use our CRH liquid antenna, indeed beta can be also modulated, right? It's just that beta now can be both positive and negative, right? So yeah, so here if we still let it be a binary modulation, so in this case you can imagine that or assume that 0 is negative beta and 1 is positive beta. So if the spatial distribution of beta is like is also changing with respect to the time, right? Then we should be able to control not only fundamental tone but also as well as the harmonic index as well. So all these can be digitally controlled by FPGA shown here. So then yeah, we did some theoretical analysis first, right? So then indeed, if we provide different space-time coding metrics, we can not only control the fundamental, but we can also change its harmonic beam directions. Yeah, so later on we'll see how we can utilize this to basically apply this concept into the secure communication. Another interesting property is that this kind of space-time modulated liquid antenna can provide a non-reciprocal property, right? So such that, for instance, if we choose the center space-time coding matrix, right? So if we inject F0 tone signal from the antenna port, so you can see here the F0 plus delta F will go to this a little bit tilted direction, so it will go to this direction, right? So this frequency is the first harmonic F0 plus delta F. So delta F is the modulation frequency of the FPGA. So this is in the transmit mode. In the receive mode, if we still inject F0 plus delta F, actually at the antenna port, what you will see is not F0. It will actually give you the second harmonic, which is F0 plus 2 times of delta F. Yeah, so this is because the space-time modulation, depending on the different angle, right? So because now in the receive mode, we are illuminating at the positive harmonic angle, so we will add another harmonic index onto it, so +1, and then you add another 1, so it becomes +2 harmonic. Yeah, so by doing this, actually we can separate the transmit and receive signal easily by using a filter, right? So this will enable the so-called simultaneous transmit and receive. All right, so yeah, having introduced some fundamental properties of this liquid antenna and CRH, and then also how we can do the space-time modulation of a CRH liquid antenna. So now we're gonna talk a little bit more on the application scenarios. So yeah, actually we just talk about the frequency space mapping characteristic of liquid antenna. So this phenomenon can be observed in the optical regime as well. So if we have a broadband optical pulse, right, if we inject this into a grating structure, so we know grating can also function as a frequency space mapping device. So you'll see that so this rainbow color indicates different frequency component will be mapped to different location. So if now we have like a barcode structure, right? So some part of it, they have different reflectivity. Then you can imagine some part of it will be metal and then other will be dielectric, something like this. So therefore, because of this different reflectivity, what we need to do is that we can measure the reflected spectrum, right? And then by mapping this frequency component to its corresponding angular direction, then we can reconstruct the image almost instantaneously, right? Because everything now is done in an analog domain. So indeed, this kind of mechanism can be used to break the so-called trade-off between the speed and field of view, because now the scanning speed basically, right, is instantaneous because you just map the different frequency component to different angle, and then you pretty much just read out the spectral component. You can immediately know where the target or the DUT is located, right? So yeah, so then this also makes us think that we can use a similar property, right, on our liquid antenna, right? So now we have a X-band CRH liquid antenna and this is a dispersion curve, right? It's from roughly from 8 to 13 gigahertz. And then you can see how the main beam angle can scan. So if we have liquid antenna, put it here, and then we connect it to a VNA. We also have another whole antenna as a receive antenna. Then by putting the target at different angular location, we should expect we can see a peak at different spectral component, right? So for instance, if we put our target in the middle, we should expect the center frequency will have a peak, right? And then if we put our target in the forward side, and we see the high frequency as a peak, right? And on the other hand, we put the target the backward side, and we see the low frequency will have a peak. And this concept can be extended to multi-target detection as well, right? So we have multi-target, and we do see two peaks in this case, and we just need to simply map this peak to the angular location, and we can know immediately where the target is located. So this scheme allows us a very simple sensing detection method, which does not really require any mechanical rotor for scanning, and also there's no phase shifter like what we have used in the phase array. So so following this concept, right, we first just built or designed a 24 gigahertz material liquid antenna. So as you can see here, so this structure is a little bit different than the previous one, but still, basically the equivalent circuit model is the same. So in the middle, you can see this gap capacitance, right? And then here, this huge patch, it serves as a virtual ground to form the stop inductor. So using this, we can realize the 24 gigahertz CR liquid antenna, and as you can see here, when we scan different frequency, indeed, we can see a main scan. So we utilize we basically put this material liquid antenna, and then we connect it with a commercially available 24 gigahertz radar sensor chip, right? We connect it to its both transmit and receive port, right? And then this radar sensor chip can generate both in phase and quarter phase signal, right? Also called IQ signal. So once we have this IQ signal in phase and quarter phase signal, then we are able to obtain the phase information. And then we can incorporate this arctangent demodulation, right? So by taking arctangent of Q over I, then we can obtain the phase. So we know phase has a relation with the target's displacement. Basically, it's following this 4 pi, because it's the round trip by 2 times 2 pi over lambda, and then times this x is displacement, and then plus some residue phase, right? So by doing this means that if we have the phase information, then we can also connect it, right, or refer its displacement information. And furthermore, if we just do some Fourier analysis, then we should be able to obtain the vibration frequency of the target, right? So we utilize this to conduct human vital sign sensing. So by using that radar sensor, yeah. So we basically have in this scenario have 2 targets, and then we just change the center frequency, so we can for target B, right? It's operating at 24.3 gigahertz, and then for target A, we just steer the main beam, right, to let it be point to let it point to the target A. So at a higher frequency. So then, so the first 2 figures, these are IQ, and then after taking arctangent demodulation, we can obtain the phase, right? And after some signal processing, including Fourier transform and then some filtering, then we can obtain the target's respiration rate, the breathing rate, and then heartbeat rate, respectively, for the 2 targets with a pretty good accuracy, pretty small error. So because we have the displacement information, we can also obtain, if now the target is moving, we can also obtain the relative movement of the target. Yeah, so here is the movie, right, showing that the 2 targets, they are coming back and forth, right, or moving back and forth towards the radar sensor, right, as you can see here. Yeah, and then because of this, right, so we can reconstruct the 2 people's relative movement from different angle towards the target, right. Okay, so then the next, so having discussed about the first radar sensing scheme, right, that was based upon a straightforward homodie radar sensor. So the next architecture I'm going to talk about is going to be based upon this self-injection lock mechanism. So as you can see here, when my hand is moving, right, it's a little bit slow, but yeah, when my hand is moving, you can see the center frequency of the oscillator is keeping changing. Yeah, from the spectrum analyzer, you can see that when my hand is moving, right, the oscillator frequency is actually keeping changing. It's not very clear, but yeah, let me try to replay the video again. If we look at that oscillator, you can see tiny changes for the oscillator frequency. And this is because when my hand is moving, right, the injected signal, the reflected signal will be injected into the oscillator again, and which will cause the frequency change. Right? So that means, right, so that frequency change, the changing rate of the frequency, right, should be corresponding to my hand's vibration rate, right? Yeah, so therefore, if we can do some frequency demodulation of this self-injection log radar, we should be able to also obtain the vibration frequency of the target, right? So it turns out that this displacement, delta X shown there, is actually related to the frequency change, right? So yeah, so indeed, what we'll see is that you will see a constant frequency change as the target is vibrating, right? So yeah, so this relationship, this injection log relationship is governed by the so-called Adler's equation, where the logging range, right, meaning that how much the frequency can change is proportional to the, of course, the injection power. But good thing about this is that the Q factor of this oscillator doesn't have to be that good because it's inversely proportional to the Q. However, so one advantage of this self-injection log radar or SIO radar is it's immune to DC offset caused by steady target or tissues. Because if the target is not moving, actually it won't cause any frequency change of the injection log oscillator. But then one slight drawback is that since it's still require sufficient injection power to make the locking range huge, yeah, so this might be, if we want to really go to a super high sensitive radar sensor structure, that means you still have to have a sufficient amount of injection power. But we still utilize this self-injection log sensing scheme, and then we connect this to our metal liquid antenna, right? So now that we have a frequency scanning antenna, so the frequency is from 1.8 to 2.8, right? And then we connect it to a self-injection log oscillator. And here we also have incorporated a material transmission line based coupler to couple a little bit amount of the signal out to the frequency differentiator. So this frequency differentiator can allow us to perform the frequency demodulation. And then we run it through a envelope detector, and then we will obtain the baseband signal. And then we can do some further signal processing, right? And this is a prototype that we built in-house using PCB board. So we have two targets we still have two targets sitting in front of the radar sensor. And yeah, they sit at different angle and different distances. So first, of course, we can do the same thing, right? We just change the center frequency and then we can steer the main beam, right? So then, yeah, as you can see here, we can obtain the different once we do the arc-tangential modulation, we can obtain the phase information, and then later on, we can do some signal processing to obtain the two targets corresponding with respiration and heartbeat rate. And yeah, once we compare with the ground truths, it still have a pretty good accuracy. But so far we have just tried to detect their vibration frequency and angular location, right? But in the meantime, we would like to also try to see if we can obtain the distance information. But then since we operated previously in the continuous wave mode or CW mode, we know that CW radar can not really provide us with the absolute distance, right? So here we incorporate the frequency shift key modulation or FSK modulation. So we just let two frequencies, right, very close by two frequencies, they just toggle between each other. So these two frequencies is just separated by a couple megahertz. So the main beam direction won't change that much, but then if we look at the Doppler spectrum, the peak of the magnitude will appear the same frequency spectral component. But then if we look at the phase, so the phase will have the tiny change because phase is pretty sensitive to the frequency. Yeah, so this delta theta, which is the phase difference between the two tones, can be related to this equation shown here. Yeah, so because of this lambda 1 and lambda 2 difference, then it will result in this delta theta change. And from this delta theta change, we can calculate this distance information, right? So d will be related to this equation shown here. It's a speed of light times the phase difference and divide by 4 pi, and then times this delta f, which is f2 minus f1. Yeah, so by incorporating this FSK modulation, then altogether, right, plus the frequency scanning capability of the liquid antenna, so we can obtain not only just angle vibration, but also the distance information with a still pretty decent accuracy. So this is a summarizing table for your reference. So recently we have tried to also scale up the frequency from lower band to higher band. So here is shown here is a 85 gigahertz self-injection log radar sensor using gallium arsenide 0.1 micron PHEM technology. Yeah, so here everything is integrated into one single chip, and the chip size is 3 by 4 millimeter. And so we have an on-chip antenna, right? And then here we have a transistor. And then, yeah, we have, this is a coupler, right? To couple out a little bit of energy to the probing pad. So put this chip on the probe station, and then we measure, we still have a target sit in front of the radar sensor, right? And then at different distances, and we try to measure his respiration and heartbeat rate, and still we can obtain his vital sign pretty accurately. So yeah, so far we have mentioned two kinds of radar sensing scheme, right? The first one is the traditional homodie architecture using a commercially available radar sensor, radar IC, right? And the second one is it's based upon the self-injection log mechanism. So the third one we're going to talk about is based upon this so-called supergenerative receiver. So this supergenerative receiver or SR receiver has been used for a long time in this wireless communication to realize this a simple wireless receiver, right? So what this does is that you can imagine this supergenerative receiver is it has a time varying loop. Right? So meaning that it's like an oscillator, but then this oscillator is being turned on and off, right? So therefore, if now there's no incoming signal from outside, so basically it has two modes. In linear mode, the oscillation will become very weak, but then once it receives some signal coming from outside, then you will see a strong magnitude for the next oscillation period. On the other hand, if we operate in a log mode, right? So even if there's no incoming signal, you will still see an oscillation. But then once it receives some signal from outside, in the next period, you'll see the oscillation period will become a lot longer, right? So yeah, these are the two modes, fundamentally two modes for this SR receivers. So this makes us think that, okay, so if they have this property, right? Particularly in the log mode, right? If we have a constantly vibrating target, then we should, in time domain, we should expect this oscillation should change as well, right? With respect, and then it should be also in a periodic fashion as well. So yeah, so we try to build a prototype to verify the concept. So we have a 2-port patch antenna, and we connect it to a transistors to make it into a active antenna. So then we can have a quench signal to modulate this oscillation, right? So if we have a receive signal and then we operate in a log mode, right? So if the receive signal is small, then we have a shorter oscillation period. But once it has it sends a stronger receive signal, then basically the next oscillation will become longer. So if this receive signal is also a periodic signal, then we should see our alpha oscillation should be a periodic waveform, should have a periodic waveform as well, right? So actually in log mode, we can approximate this relationship using this exponential function. So yeah, so depending on the build-up voltage, right? So basically in the end, they will all grow to its saturation voltage, right? And during this period, from the initial to this equilibrium voltage, we can use a simple exponential function to represent. And then by also combining the radar equation, then we can obtain from different for different initial voltage, right? We figured that if delta x is much smaller than the distance, actually it's going to be we can approximate as 2 delta x over r over the distance, right? So combining the two, we can obtain this relation such that the delta t, which is the difference in the oscillation period, is related to the delta x, which indeed is displacement, right? So yeah, so since they have a linear relationship, delta t and delta x, then that means we can also do a simple Fourier analysis to obtain the vibration frequency of our target, right? And the advantage of this SRO radar sensor is that it has this intrinsic automatic gain control. Regardless of how tiny signal initially it is, it will always grow to the equilibrium voltage, to the saturated voltage. And there's no null point DC offset for this radar sensor because yeah, everything is just based upon initial condition, right? So then, yeah, so we fabricated a prototype to verify this. So this active antenna is oscillating at 2.3 gigahertz. So you see we have a peak here, and then it has a broadside radiation. And then, so first we utilize this to detect the actuator's vibration, right? So the displacement of the actuator is around 3.3 centimeters, and the frequency is 1.25 hertz, and distance is 2.8 meters, right? So then we compare with the SIO mode, right? So indeed, the left-hand side is SIO mode. So indeed, we use our SRO radar sensor to detect. We do see a gain increase, roughly from 5 to 7 dB gain improvement as compared with the SIO radar sensor. And this is again because of this sensitivity period that we have, right, from the buildup of the oscillation, right? So which can provide a high sensitivity. And then we also utilize this kind of sensing scheme to detect human vital sign, right? So then we have a human target sit in front of the radar sensor again, and then we at different distances, and then we compare with the SIO mode. So at the shorter distance, 1.2 meters, both of them, both SIO and SRO mode, they can successfully detect the target's respiration and heartbeat rate. But then once the target is further away, then you see the SIO mode will start to have some difficulty. By SRO mode, because of it has this sensitivity period when it's trying to build up, then we do see a stronger signal in this case. Yeah, so here is a summarizing table. Yeah, as you can see at the shorter distance, both can perform well. But then once the distance is longer, then we see the SRO will outperform SIL, right? By this higher sensitivity. So the next thing we did is also we connect our magnetron antenna with this SRO radar sensor, right? So we have additional quench signal. So I believe this is coming from the drain side of the transistor, right? So we can modulate this oscillator. Then because of this frequency scanning property, we can utilize this to again detect multi-target, right? And yeah, then we can, after doing some signal processing, we can successfully reconstruct their respiration and heartbeat rate respectively. So yeah, here we also compare, in this case, we also compare with the SIO-based radar sensor. Yeah, so as you can see here, the SRO radar sensor can still have a better performance with less error and better accuracy as compared to the SIO mode. Okay, so then since we have talked about the SRO mode, right, and so far we have just mentioned how it can be used to detect the vibration frequency, right? But still, we would like to see if we can obtain the distance information, right? So yeah, so actually we found that the SRO radar sensor is pretty similar to pulse radar. So then if we have a way to know the time of flight of each pulse, right, then we should be able to calculate the distance of the target as well. So it turns out, yeah, so we use this time domain cross correlation to figure the time of flight, the round trip time of each pulse. So once we have the round trip time, then we can calculate the distance by using speed of light, right, times this delta t and divide by 2. Then we can obtain the location information. And vital sign, we can just use the signal processing mechanism that we have utilized before just by using this simple FFT, right? Then we can obtain the vital sign information. Yeah, so together, right, we can obtain multi-target vital sign location information. So here we have 2 targets sitting in front of this SRO radar sensor, and then we have another receiver to enable the calculation of the round trip time, right? So yeah, so indeed we can obtain the distance and then breathing rate and heartbeat rate. And again, the frequency can be mapped to the angular location. So we can obtain the entire information of the 2 targets. Then in addition to the far field application, which is just radar sensor, this SRO-based sensor can also be utilized in the near field, right? So this is a oscillator, but then this shown here is SIW, or substrate integrated waveguide based cavity resonator. So this is not an antenna, but on top of it has some slots. So it only allows a portion of the energy leak out to the near field. Yeah, so therefore we can, by operating in the SRO mode, right, we can utilize that mechanism to sense tiny vibration on top of our fingertip, because we know our fingertip will have some tiny vessels, right? But SRO sensor, since it's pre-sensitive, we can detect the tiny movement on top of the vessel. Yeah, so as you can see here, we compare it with the PPG sensor. So yeah, roughly, if you compare the beat to beat waveform, they match pretty well with each other. So after doing the Fourier analysis, we can obtain the heartbeat information as well. So yeah, this the material concept. So far we have just use it in the one-dimensional scheme, right? 1D or 1D scheme. So it can be extended to 2-dimensional as well. Suppose our feeding network is also based upon this CR transmission line, because as we mentioned in the beginning, right, this CR transmission line can provide both positive and negative beta, which is equivalent to positive or negative phase delay or phase events, right? So then basically in this case, right, if we scan the frequency, it will allow us to not only scan in this YZ axis, but in XZ axis, right, in XZ plan, right, can also provide some scanning because of this phase delay and phase events. So together you will see this membrane direction is not only changing horizontally, right, but then this in the vertical direction it will also change. So it will be this zigzag fashion. So we also did it in the 24 gigahertz band. In this case, we use a long transmission line to behave as a feeding network. It can also provide the required phase that we need, but just in this case, you just need some longer transmission line. Yeah, here we have 4 antenna elements. So as you can see here, it can also indeed provide a 2-dimensional frequency scanning capability. So we utilize this to also detect multi-target vital sign signatures. Yeah, so because now the antenna array can do 2-dimensional beam scanning, so one target can be standing, the other one can be sitting. As long as we pick the same frequency, then we can accurately illuminate the main beam to the 2D space, right? To map to the chest direction. Yeah, so as you can see, we can also accurately detect their respiration rate, heartbeat rate, respectively. So yeah, in addition to radar sensing, we also utilize the liquid antenna to do some imaging. So if we have an array of material liquid antenna, right here we have 16 array, and because of this frequency scanning property, if we have 3 cylinders like this, right, stacking up with each other, then basically different frequency will be pointed to different cylinder if we choose the correct frequency. And once we choose the operating frequency, then we can perform. So this becomes an inverse scattering problem, right? So we can from the scatter E field, then we can utilize to solve this inverse scattering problem, we utilize a so-called linear sampling method. So it's a qualitative method in order to solve for this inverse scattering problem to reconstruct the image. Yeah, so first we use the ideal approach. This is the ideal scatter field of the cylinder in terms of Hankel functions. Yeah, so then at low frequency, right, we can see, right, at low frequency, we can obtain the 2D cut of the bottom cylinder, and then at center frequency, we can obtain the 2D cut of the middle cylinder. And then at the high frequency, you can obtain the 2D cut of the top cylinder. So we did some experimental verification to validate our concept, right? So we have 3 cylinders stacking up on top of it, right? And then we have, here we just use one material antenna, but we manually rotate the arm, right? So we can still gather the scattering information at each angular location. So yeah, indeed, by solving the inverse problem at different frequency, we can reconstruct the bottom cylinder and then the center cylinder and the top cylinder quite nicely. All right, so then so far we have talked about applications and sensing and imaging. So the next topic I would like to also talk about is how we can apply, concept of materials, particularly in the application for secure communication. So we know that over the time, right, when we have a transmitter and we have receiver, we only want our legal receiver to receive the correct information at the all unwanted direction. We don't want them, particularly if they are adversary or eavesdropper, we don't want them to listen to what we are sending, right, or what we're talking about, right? Yeah, so one technique here is called directional modulation. It can enable this kind of phenomenon or characteristic, right? So basically, it will distort the signal in all unwanted direction, while only allow the correct signal to be transmitted in the wanted direction. And because this, and because this is happening in the physical layer, so it can provide us with pretty secure communication. So one way to do this is if we have a time modulated material antenna array. So here we have, as you can see, we have 4 antenna array, right? And then we connect it with a phase shifter. So by doing this, right, as we just mentioned, a CR Schlegel antenna can do frequency scanning. So it can scan on the YZ plane. So by adding this phase shifter, it can allow us to also change in the XZ plane. And on top of this, we have switches, right? And these switches are not going to be turned on and off at the same time, right? So so basically, they will be turned on and off. If we design this switching waveform properly, they will be turned on and off in a different time slot. But this will allow us to basically enable the so-called directional modulation. So at the desired location, the signal from all those 4 branches will sync together. But then at the all unwanted angle, you'll see the distorted signal. But of course, the assumption is that you have to design this switching waveform properly, right? And this is the waveform that it shows here for different time slot and different location of the antenna element. So then we build a prototype to verify this. We have 4 antenna element array, right? And then we connect to a phase shifter, and then we design a power divider. And then it's connected to a switch, and then we use function generator to control the switch. So you can see here, here we compare the bit array with and without the directional modulation. So yeah, without directional modulation, it acts as a conventional phase array. So you can see the bit array angle is pretty wide, meaning that, so this, suppose this is our desired angle, right? But if we have a very sensitive receiver, let's say just a little bit away from the desired angle, it can still capture the information, right? But once we turn on that time modulation, you see, this will enable the directional modulation. You see the bit array angle will become a lot narrower, right? And this will make the other angle pretty, you basically make the other angles bit array very high. So therefore, if we have adversary at other directions, it will be very difficult for them to detect the signal. So then, on the other hand, right, this can be also achieved by using our previously proposed digitally space-time coding material antenna array, right? So like we just mentioned, if we have the correct space-time coding matrix, right, we can basically not only control our fundamental tone, which is associated with our information, right? But we can also send a bunch of harmonic tones to other directions to distort the information. Yeah, so if we have the correct space-time encoding matrix, we can actually achieve this. We can send the correct signal to this Alice location, right? And then all on one angle, we will distort their information. So yeah, this is still based upon the binary space-time encoding matrix. You can imagine 0 is where beta is smaller than 0 is negative and 1 is positive. But of course, to obtain this space-time encoding matrix is not trivial, right? We actually utilize some machine learning method to obtain this space-time encoding matrix. Yeah, so then here is some theoretical analysis, right? So yeah, so if we have 9 unit cell, right, and we see the fundamental tone is at the broadside, and this new indicates harmonic beams, right? So we will have a harmonic. So at the broadside, you see all the harmonics will be suppressed, right? But then at all other angles, we see higher harmonics, and this will enable the secure communication. And if we have a larger antenna aperture here, we double the size of the unit cell, right? You see we can have a more directed beam. And on the other hand, we have more, larger numbers of the unit cell, then indeed we can increase the harmonic level to enhance the security. And also by changing the space-time encoding matrix, we can change the main beam direction as well. Yeah, so this can provide us with a pretty powerful platform to enable main beam control and also harmonic beams control. All right, so then, yeah, here is the comparison table, right? So with and without the beta array, you see some change, right? So yeah, with once you turn on that directional modulation, you see the beta array angle will become a lot narrower. And by using another set of space-time encoding matrix, we can change the main beam direction as well. And here is the beta rate of Eves and Bobs, right? So yeah, so Bobs is the legal receiver. So once we increase the SNR, you see the Bobs as a bit array will become a lot smaller, while Eve's direction is still has a pretty high beta array. And yeah, as we just mentioned, because to obtain this, it is not trivial to obtain this space-time encoding matrix. So once we incorporate the machine learning method, we can actually improve this calculation speed by approximately 40 times faster. And we also did some experimental verification to validate the concept, right? So here we built a 9 unit cell, digitally modulated space-time encoding linked antenna. So we have 2 sets of space-time encoding matrix, right? Correspond to this is simulation that correspond to different main beam angle and different level of harmonics. So as you can see here, we also have the measure beta array. So you can see with and without this directional modulation, the beta array angle does show you a huge difference, right? Once we turn on that the directional modulation, the beta array angle become a lot narrower. And by using different space-time encoding matrix, we can see the main beam will change, right? All right. So yeah, last but not least, we have also, so recently we know there's a huge boom in AI and machine learning, right? So, but those are typically seen in the digital domain, right? So here, what we're trying to do is we try to build a microwave version of neural network. So if you look at each neuron, so we know neural network basically is just what it does is multiplication and summation, right? So this can actually be done in the analog domain, particularly using microwave circuit, a simple microwave circuit. So here we have 2 couplers and then 2 phase shifters. So by changing the phase shifters, actually we can just control the weighting of this analog neural network. So if we have several of them, we can put together a analog processor, right? So by changing the weighting, by giving the neural network proper weighting coefficient, then we can do a simple minutes test. So suppose we have a digit 9, right? And then we first encode it into microwave signal. And if you train this microwave neuron well, then what you will see is that at port 9, we should see largest signal or strength or magnitude in port 9. So this can give us instantaneous classification of the digit, right? And the advantage of this is it's very low latency. Everything is in the speed of light, and also power consumption is very low because we are only use phase shifter. If we use varactor, then it can have very low energy consumption. Okay, so to conclude, we talk about material-based 1D, 2D beamforming, and then we utilize frequency space mapping to allow us to do remote sensing and tomography, right, with fast sensing speed and large field of view. And then we also talk about how we can utilize the space-time modulated antenna to allow us to do physical layer secure communication. And we hope that by using the proposed metamaterial related component and circuitries, we can do more new applications in the field of sensing and communication, and also computing, like we have just mentioned in the end. Okay, so because this is an MTTML talk, so yeah, what I'm gonna do is I'm gonna do a little bit of promotion for MTTS. Yeah, I'm sure some of you may be an MTTS member already. How many of you are MTTS member? Maybe that's a question. Oh, you okay? Good. Oh, so you're not. You're AP. Okay.
For MDT, I'm only for APS.
Sorry to hear that. Will you consider?
Yeah, here combined, but you are becoming one member, so it's okay.
Oh, I see.
Here initially combine AP slash entity slash E.
Oh, so this chapter is combined. Okay, good. Right.
EMC.
Oh, so that's a lot. Okay, I see.
Because here our percentage is not very big.
Right. But you have so many students.
But they don't want to join because of they have to pay.
Oh, I'm gonna talk about this. So if you're a student, you can pay less than $1 to join MTTS. Yeah, I think here it depends on region. I think that $1 probably is region one.
$82.
Huh? $1 or less than $1.
Yeah, but the for IEEE members, $32, right?
That is true. They have to closely come.
Yeah.
Student member, but that student member should have some discount also. Yeah, so maybe it's something worth considering. Yeah, but if once you join MTTS, it will provide a lot of opportunities, particularly networking and career development. So here are some publications related to MTTS, right? Like magazine, and then TMTT, Transactions on Micro Theory and Techniques, NWTL, the letters, and then terahertz and Journal of Microwave, and then there's much more. There's also one related to biomicrowave, right? And yeah, a lot more. So there are some major conferences sponsored by MTTS. The first one is IMS, International Microwave Symposium. So it's the largest one. Typically, we'll have more than, I would say, 10,000 attendees, and then a very huge exhibition. So this year it was in San Francisco. Next year it's going to be in Boston. And so this is in summer frame. In winter, there's another one called Radio Wireless Week, RWW. It consists of 5 sub-conferences. You can see here, RWS, PAWR, another one related to wireless sensors is called WISNet, and then SURF is more related to silicon IC, and then another one related to space applications, right? And yeah, so this one is going to be named next January in Los Angeles. So these are the main 2 flagship conferences for MTTS. I know AP also has APS, right? ERSI APS. This year it was in Ottawa, was it? Yeah. And next year it's going to, no, APS, antenna, Ottawa, right? Next year it's going to be in Detroit, right? That's what I heard. Okay, so, what's that? Oh, 2030 will be in Sydney. Oh, wow, okay. Are you involved with that? How do you know? How do you know 2030 is coming in Sydney?
Professor Caro.
Oh,
Send me the
Cameron?
Caro Ezel.
Oh, nice. Okay, cool. Cool. 2030. Okay.
I think so, if I'm not mistaken.
Okay, cool. And yeah, over 40 MTTS related conferences, not just these two, but much more. I think I'm not sure APS is also related to probably MTTS, but so yeah, there are also local MTTS chapters like this one, right? And also student chapters, student branches. Yeah, I don't know if there's a student branch in UTM, but if not, maybe can consider to form one.
Yeah, but no chapter.
Oh, there's an IEEE student chapter here. Oh, then it will be very easy to form a MTT, join the MTT AP.
If you can pay to them, it's okay.
No, right, but you should be able to get some support also from IEEE section to form a chapter. Yeah, so, but, right. So then, yeah, a lot of volunteer opportunities, and then, yeah, so another incentive is that if you are a first or second year PhD student, or even undergrad, right? Undergrad, you will have this fellowship or graduate student. But if you are a PhD student, particularly first or second year, and you have never attended IMS or WW, so we have this, recently there's this PhD initiative program, which can allow you to travel. So MTTS will reimburse you with travel expenses. So which can encourage students to participate in MTTS conferences. Yeah, and then there are also other special interest groups such as young professionals or YP. Yeah, I know APS will have the same thing. Yeah, so if you are YP, meaning 15 years after your first professional degree. So in this case, in our case, engineering case is always bachelor. So 15 years after bachelor, you still consider YP, and you're eligible to join the YP group. And then there's another women engineering. So I think it's also another thing that IEEE is promoting right now. And then site, yeah, site is more like a humanity or no, so to promote some underrepresented areas, and then also life members benefit. Yeah, so for more information, then feel free to check out our the website of MTTS. Okay, and I think, yeah, thank you. Terima kasih. And I,
Dr. Mike, you didn't mention about what is the advantages of using the MPM towards the select group.
oh, yeah, okay, I was gonna talk a little bit about our school, but. Yeah, so advantage there are a lot, right? So basically, yeah, so if we use materials, actually we can control the EM wave in a finer scale, right? Because each unit cell is much smaller than the wavelength. So we have more accuracy and flexibility to control the EM waves property, which cannot be done by using the conventional way of the antenna array, right, or reflect array, because reflect array ideally or theoretically is just half wavelengths apart, right? But if you make the unit cell, right, like either metal surface or metal material antenna, if each unit cell is much smaller than wavelengths, then you have a better capability in terms of controlling the reflection or radiation of.
What the size will be more small or?
It depends on the frequency of operation. Yeah, so yeah, but yeah, if you want to have, let's say, there's always trade-off, right? If you have larger aperture, then of course your beam will be narrower, right? But yeah, if you want to have a better, capability of controlling the EM waves.
Is just easy.
Huh?
The main advantages is easy.
Material, yeah. It will provide you a better capability of controlling the reflection and then also radiation in that sense. And then plus we talk about space-time modulation, right? If you also modulate it not only in the space domain but also in time domain, then you have more flexibility to control the EM waves. So that this is not something can be done in the traditional way, right? So then Yeah, I would like to also, hey, can I see my, oh yeah, good. So we still have some time, right?
Something.
Oh, okay.
Just now you mentioned about the entity.
Yeah.
Because I came. Because I think you did mention about the journals which are the entity. But I think in your slide, I think I can see that you also presenting about the data.
Oh, what's behind?
There's one publication.
Okay, you mentioned about the MWPL, right? Yeah.
Yeah.
But I think your work here, I think I saw that you are doing something on antenna. Yeah.
Antenna, that should be more APS related journals.
So in order for us to get our publishing, IEEE.
Yeah, so the rule of thumb is if it's just a pure antenna, right, usually it should be submitted to APS related journals.
Okay, so to qualify this one, you should have what
Some microwave components. Yeah, not just pure antenna. Active antenna is okay. Or
anything which is outside.
something in addition to antenna is okay.
In addition to
Yeah, like system or phase array, that should be okay. Yeah.
So, for example, let's say you're talking about the phase shifter or
Yeah, phase shifter is okay, definitely. Yeah.
so anything for theory. Okay.
Right. If it's a pure antenna, passive antenna, it's better to submit to TAP. Yeah. Okay. So I'm gonna talk a little bit about our school. If that's okay. Hey, Professor Kamal, are you? I'm gonna introduce a little bit about. Okay. See you later. Okay, so yeah, basically, so I'm from National Taiwan, right? So we have this Graduate Institute of Communication Engineering. It's founded in 1997. So we have three groups, right? EM groups, and then Communication and Signal Processing group, and then Data Science group. So yeah, these are some faculty and student numbers. Yeah, so I'm from EM group, so mostly we're working on EM related stuff, right? Like ICs and then antennas and then theory and then packaging, right? So we also have another group doing more like signal processing stuff, like medical imaging and then communication, right? So recently, there's a huge conference. It's called it's in Taipei right now. So almost all the area, all the faculty in this area are attending the conference right now. And there's also data science group. So right now we know machine learning is very popular. Yeah, so a lot of faculty members are working on machine learning and then computer vision. Yeah, in this group. And yeah, we have several awards from both professors and students, and a lot of honors. Right, we have quite a bit of IEEE fellow, ASM fellow, and editor-in-chief. Yeah, so it's the IEEE fellow stats. If you compare us with other leading universities over the world, yeah, we're in a good shape, right? We're even better than some of the schools in the US or in the other areas. Yeah. So very high job security. Yeah, I think now TSMC, right? Taiwan Semiconductor Manufacturing Company becomes pretty famous over the world. So most of the students can get a job in top companies in Taiwan, particularly in TSMC. We also have MediaTek, which is an IC design house, right? It's also has a very good market share. So a lot of top companies in Taiwan actually over the world, like Asus is a leading PC or laptop companies, right? And Delta is a power supply company. So because of recent boom in AI machine learning, so Delta is also doing very well. And TSMC, of course, top one pure play semiconductor foundry, media one number one chip designer, and then we have Quanta Computer. Yeah, so basically it makes notebooks for or laptops for other people, and Realtek and then Foxconn, much more. Yeah. And also Win Semiconductor, I don't know if you heard about it. It's also the largest pure play 3.5 foundry in Taiwan. Yeah, so we do have a lot of international students activities and in NTU. Yeah, so it's a lot of fun. Yeah, so hopefully we'll have, talking to the students, yeah, if you have a chance, feel free to let me know. And yeah, we also have students, I think we do have some students from Malaysia, and yeah, so thank you. So if you want to know more information, and check out this video. Okay, so I'm open.
I think Q&A session. So if you have
Yeah, I'm.
Yes.
Just now you mentioned about the AI and machine learning.
What's that?
AI, machine learning.
Oh, yeah, machine learning. Okay. You mean for in our school or this one?
Yes.
Okay.
So I think, when we mention about machine learning and AI, are you talking about machine learning and AI? Because here we have like computing of AI.
Okay.
They're doing a lot of other things.
Okay.
So, so what by machine learning and AI? Is it specific?
This is a group, yeah. But I think NTU now is also trying to form a AI institute, which will be at the university level. So this is under GIC, Graduate Institute of Communication Engineering. So this group probably, I would say, maybe about 10 to 20 faculty members in this AI machine learning group or data science group. But then what they're trying to do is they are still, this is still under discussion, but they are trying to form a university level of AI institute, which will have more faculty members involved. Yeah.
Assalamu alaikum, Prof.
Yes. So
Yes,
maybe
sir.
someone online would like to ask questions.
Yes, Prof. Can we get the video recorder of this meeting?
Oh, that I don't know.
Recorded video.
I don't know who's in charge of this.
yeah, we provide audience. Yeah, we can provide
Oh, there are 79 online. Wow. Very huge number. I'm very surprised.
our online participant. If you want to ask, just unmute and ask question directly. Any question? No? Any question from online audience? No?
You have a question? Yes. Good to see you again. Okay. Okay. Oh, no, some of them are from signal processing, but we do build a lot of hardware, right, and IC designs. What's that? Right, so we're mainly focusing on hardware, but because we are doing this radar sensing stuff, but we need to gradually shift to signal processing as well. Exactly. So yeah, so right now we do see we are not only just working on hardware, but we do have a need to integrate entire system. So that will require both algorithm and then hardware design, all of them. Thank you.
Question? I would like to ask, so hybrid RF and optical system are becoming more relevant.
Right. Microphotonics.
Yeah. So how do you see artificial material contributing to this integration?
Oh, that's a good question. I think there should be still some application, particularly material can be applied in optical domain as well, right? So it depends on if you want to control your like the light communication you just talked about. You can also use material to control the reflectivity and so on, right? To change the characteristics of optics, right? So then that's one thing. And then also if you want to use once it's down converted to microwave, right? And there are also some application that we can apply this microwave nanomaterials to it, right? To better control the properties of EM waves. So I think there is a lot of these opportunities. Oh, even for microwave photonics.
You have a friend working on optical RS, for example.
Optical risk, yeah, I do know some of my colleagues they're working on this, right? So because there's a lot of infrared risk, infrared metal surface, right? And infrared is another pretty useful frequency regime that people are talking about, because it can also allow a lot of the sensing and detection and stuff.
So last call to our online audience. Is there any question?
Oh, sure. Yeah.
Online.
I know. Amazing.
Show the slides, the job security from Assoc, Assoc, Realtek, MediaTek, right? They are popular Chinese companies based in Taiwan.
Hold on. This one?
The job security.
Yeah, this one. This one. Yeah. Yeah, we now we do have some cooperation with one of these companies. Yeah. Listed here. Yeah.
Okay.
Oh, there are some questions on. Okay. Wait. Huh? What's that?
Extend the opportunity that Olympics will be with us.
Sure. Yeah, that can always be, discussed. Yeah. Yeah. Send me an email. We can initiate a separate discussion. Hey, I saw another question online, right? Morning, Professor. Any help from metamaterial was? Oh yeah, of course. Yeah. It's a good one. So for wireless power transfer, right? WPT, right? People have been using metamaterial again to better control like a membrane direction, right? To improve the entire system efficiency. Yeah. So that's definitely yes. Yeah. And then I think MTTS is also sponsoring a couple of WPT conferences. Yeah. So if you have, if you want to know more, then you can refer to this wireless power transfer conferences. Yeah, and then you will find out that a lot of papers they are already using this material concept to form a better WPT system. Okay, thank you. Yes. I'm sorry, I understand your question. What do you mean? Yeah. Okay, maybe I can go back to my slide. So maybe I go to the meta surface one. Yeah, like this one. So what is it? Yeah. Okay. One more. Okay. Are you talking about the meta surface and metamaterial antenna? And then what? Oh, digital coding. Okay. Yeah. So this one is also okay. This one is already showing the digital coding. Yeah.
Much easier.
This is space-time coding, right? And then we use FPGA to control. So you're saying to design the code is easier? No, designing the code itself is not easy. So that's why we have to use machine learning to obtain the code. Yeah, if you really want to have a better way to match with your application. So simple coding can allow us to do simple beam change. That's also okay. But if you want to have a more sophisticated control of EM waves, then that will be a very difficult optimization problem. Yeah. So we had to use machine learning method. Yeah, so that side meta surface report. Yeah, you can build it, and it's just a risk. A lot of people are working on it. And then right hand side is our concept. We actually want to make an antenna version, right, of it. So that's why we use the CRH liquid antenna with the space-time coding metrics.
I would like to know, yeah, because just now you mentioned about the collaboration with industry.
Right.
Since you are speaking from university, right? How much actually the collaboration between universities and those industries?
Yeah, so this is how it works. So usually, the companies, particularly in Taiwan, they all have some task or some project they would like to solve, but perhaps they don't have enough, manpower to do this project. So they will offload some of their tasks to university. So our goal is to help them to solve these practical. Actually, most of the time, these problems or projects are pretty practical. They want to implement on their product like right away. Yeah. Most of the time, of course, there are some company there that is more like far-reaching. They want to do some R&D. Some of them are like this also. But I would say most of the company they want to solve for their immediate needs. Yeah, it will be more practical.
So for example, can you give example like your current work with industry, or maybe your past work with industry that you really solve the problem?
Yeah. So I can tell you. So our ongoing project is also a radar sensing project, and they also want to use like radar sensor to solve on some sensing issues, sensing problems. So we're helping them with this algorithm. Yeah.
So I think we have now come to the end of the session.
Thank you.
So on behalf of Wireless Communication Center, again, and ITB Malaysia, IP and TTT MC Joint Chapter, I would like to once again express our sincere appreciation to Mike for sharing his site with us today.
Thank you.
So, thank you also to everyone who joined both physical and online.
Online, I'm very surprised there are so many people online.
So with that, let's give one quick applause to our distinguished speaker.
Thank you. Thank you very much.
Thank you.
It's a pleasure. Thank you. Thank you. Bye everyone. Bye everyone online. Bye.
Maybe lunch? From lunch,
But dedication.